and today I'll be your host. Today we're going to be talking about elementary particles. Well, you may have noticed some new animations today, and I'd love to thank the genius creator who made them, and hope he'll make many more videos and animations to come for us. Now, it's been a while, but it's time for the magic to start, so let's get on with it. This is the standard model of elementary particles. This section here, in purple and green, is the fermions, whereas this section here, in orange and pink, are the bosons. Now, the fermions are what make up the matter in the universe, whereas the bosons are the force carriers. They take charge of the actions that happen between these particles. But something that really separates the two fermions and bosons is a special something called spin. Now, spin is a form of angular momentum, specifically intrinsic angular momentum. Intrinsic meaning inherent, fundamental. Intrinsic angular momentum is a fundamental quantum property and not related to classical rotation. Which is why it makes it so complex that you can't describe it at the spin of a globe. It's difficult to draw because if spin can only be described as an analogy, you'd have to think of the perfect analogy to describe it. So instead of going deep into spin, I'm going to explain how spin affects fermions and bosons. Now, fermions are separated from bosons as they have half integer spin. By half integer spin, it can be that spin, it can be that spin, but it can't be a whole spin. And that separates it from bosons, which can be a whole spin, or integer spin. So integer spin can be 1 spin, 2 spin, 3 spin, and it can just be no spin. The real question is, why does spin matter? I mean, I've mentioned on how important it is. Well, you could mention the conservational laws of physics, particle physics. The idea that the same amount of spin that goes in has to come out. Fair enough. But in my opinion, one of the reasons I find spin important is due to its separation between these two, because then the Pauli exclusion principle can take place. What is the Pauli exclusion principle, you may ask? Well, it basically states that two or more fermions can't share the same quantum state. So, whereas bosons can. So if I was to give you an example of fermions here, they couldn't go together and bundle up, whereas bosons can. This is such a good thing. Such a good thing. It's the reasons that we have electron shells in atoms. It's the reason that when I put my hand on this piano, it doesn't just go through it. The Pauli exclusion principle, it makes up the creation of a white dwarf star. There are so many specific uses for this principle, and I think it's really interesting. There's a lot to learn about bosons too, of course. Now, as I said, lots to learn about bosons. So, this is a helium atom. It has 2 electrons, each with half spin. Now, put their spins together and you get integer spin, making helium a composite boson. This means that they can become superfluids. If you were to cool them down, of course, turn them into a liquid, they become superfluids. They have minimal resistance. They could climb up this wall. That's the interesting thing about bosons. Let's go on with quarks. I want to go through each of the particles separately so you get a good understanding. Now, quarks are a type of fermion. You have the up charm, top, down, strange and bottom quark. Each have their own reasons for being called, although to go through a quick preview, up and down for their spin, top and bottom because it made a symmetrical idea with up and down, charm because, well, it created an idea of completeness and scientists called it charming, and strange because the way the situation it was found and the unusual longevity of life was found unusual. So that's just a quick idea of the names. If that ever confused you, now they're cleared up hopefully. An important thing to understand about quarks are they are always found bundled together. For example, quarks bundled together can make baryons. A good example of baryons are protons and neutrons. These make up the atomic nucleus, and they are the most stable example. A proton being composed of an up twice and a down once, being two up quarks and one down quark. A neutron being two down, one up. Another example of what quarks can make is mesons, which is composed of a quark and an antiquark. An example of a meson is a pion, here being your antiquark and here being your quark. All quarks have electric charge, but each have different amounts. The up charm top quark have 2/3 charge. The down strange bottom quarks have -1/3 charge. This actually happens to tell us about the charges of a proton and neutron, the overall charges, because U plus D for a proton would mean just 2/3, add 2/3 minus 1/3. That equals 3/3, or 1. So that's one charge. Whereas the neutron has D plus D plus U, or, well, U plus D, which would be 2/3 minus 1/3 minus 1/3 equals 0, which is why the neutron has a neutral charge. Before I state this, I want to go through 4 fundamental forces and add some definitions. We're going to start off with the weak force. Unlike other forces, the weak force acts over short distances and affects only certain types of particles, specifically quarks and leptons. It's responsible for certain types of radioactive decay and plays a role in nuclear fusion. For quarks, it causes quarks to change their flavour, and that can alter the type of particle they make up. For instance, a down quark. Next is the strong force. This holds atomic nuclei together, overcoming electromagnetic repulsion between positively charged protons. At a more fundamental level for quarks, it binds them together to form protons and neutrons, which in turn makes up the nucleus of the atom. The strong force is mediated by gluons, which you can see here. And finally, the electromagnetic force, which is a force that acts between electrically charged particles and is responsible for both electric and magnetic phenomena. Now you may notice I said 4 fundamental forces. And I went finally at the third. And that's because I wanted to miss out gravity purposely. Because gravity actually isn't included in the standard model. We've theorised on gravitons and multiple other ways to get it in here with a quantum explanation, but it's not included. Therefore, I only am going to be speaking for the three forces: strong force, weak force, and the electromagnetic force. Now, quarks work with all the forces. They interact with all of them: the weak force, the strong force, and the electromagnetic forces. Now, the charm, strange, top and bottom quark are basically the up and down quark. They just have a higher mass, and they're also unstable. So they would decay into the up and down quark, but can be created in high energy situations. The leptons next. The most well-known lepton is the electron. The electron has 0.511 megaelectronvolts and is one of the three particles that make up all matter alongside with protons and neutrons. They help with chemical bonding. The electron shells make a huge difference and are the reason why different chemicals and atoms have different chemical properties. Muon and tau particle are basically just electrons, just with more mass, heavier. The muon being 200 times heavier, the tau being even heavier, 3,000 times heavier. Now let's go on with the muon. The muon, which has this symbol, has a charge of 105.6 megaelectron volts. Whereas the tau, which is the heaviest of the charged electrons, is much heavier than both of these and has a charge of 1.776 gigaelectron volts. The tau is also the only lepton that can decay into hadrons, which are made of quarks. Now, the electron, muon, and tau interact with all the fundamental forces apart from the strong force. Now we've established these. What about these? This is the electron neutrino, the muon neutrino, and the tau neutrino. All different flavours of neutrinos. Now, neutrinos have very small masses and are neutral particles, meaning they don't have any electric charge. This reduces their probability to interact with matter. So loads of neutrinos are going through you right now, but they're not interacting with you. Now, the three flavours of neutrino, as mentioned, electron, muon, and tau, are determined as flavours depending on which they're associated with. So, an electron neutrino is typically formed from beta decay, which is where a proton transforms into a neutron, emitting a positron and an electron neutrino. A muon neutrino would form from a charged pion decay, and a tau neutrino would form from a tau particle decay. So, the sun is constantly giving out neutrinos from nuclear processes inside. In fact, 400 billion per second are passing through you right now. That's leptons. Next on to the bosons. We have the gauge bosons and the scalar boson. As you know, the bosons are force carriers. So the strong force is carried by the gluon, the electromagnetic force is carried by the photon, and the weak force is carried by the W and Z boson. It's important to know that the photon isn't charged, it's a neutral particle. It just carries electromagnetic force. If they were charged, they'd interact with each other. They'd be bouncing off each other, which would be very strange. Now, to give some clear definitions for the bosons, I wanted to read them off from my notebook. Now, the W and Z boson have high mass due to interaction with the Higgs field, which is a field that gives mass to other fundamental particles, such as electrons and quarks. The Higgs boson is a fundamental particle associated with the Higgs field. The Z boson doesn't carry electrical charge and it's a neutral particle. Therefore, it only interacts with the weak force. It has a mass of 91.19 gigaelectronvolts. The W boson has a mass of 80.3 gigaelectronvolts and it can have plus or minus 1 charge. So it interacts with the electromagnetic force and the weak force. A gluon is massless and has no electric charge. Photons are particles that constitute light and other forms of electromagnetic radiation. It's massless and also has no charge. Now, let's go on to this. The Higgs boson discovered in 2012. It gives mass to other fundamental particles, apart from neutrinos, which is still a mystery. Fundamental particles associated with the Higgs field, and particles get their mass from interacting with the Higgs field. So basically the Higgs boson is this excitation of the Higgs field, if that makes sense. But to give you a deeper understanding of what I mean by the Higgs field, I want to go through something I decided that we should probably keep for the end. It's called quantum field theory. And it's quite complicated, but in simple terms, it's the body of physical principles combining the elements of quantum mechanics with those of relativity to explain the behaviour of subatomic particles and their interactions via a variety of force fields. With the quantum field theory, we change the strong force to the strong field, the weak force to the weak field, the electromagnetic force to the electromagnetic field, and Higgs field. So, to go on to the final idea of the Higgs boson, it has a mass, but zero charge and zero spin. Well, that's subatomic particles. I've tried and gone into as deep as I could, and I understand that it's complicated. And I had to read a lot of books to understand them. But if you think that this video goes through everything we've learned in the elementary particles, you're wrong. There's so much more to this standard model that we could learn. We could learn about colour charge. We could try and investigate on perhaps why electron, muon, tau, neutrino have very small mass and what gives them mass instead of the Higgs field. It's all to investigate, and you may one day be the next great physicist. You may be the one who answers these big questions. Well, that's all for the video. I hope this gave you a base understanding of elementary particles and the standard model. If it was too confusing or there's something you didn't understand, please understand that you can just go back and give some research into it. That's all from me. This was the Shell Physics Show with your host, Master Physics. I hope you enjoyed.